a structural engineer with Atlas 2. We're really excited to bring you this webinar about the McKinley Grade Separation Bridge Project in Corona, California. Before we jump in, just a tiny bit about Atlas 2, but for those who don't know, we are the largest producer of HSS in North America, and we produce the largest HSS. We'll get a bit of a taste of that today. We also have some products like Shuriken, as well as some software to make it easier to work with the products. As far as this webinar series goes, it's something we started recently. Our goal here is just to bring you interesting projects that are presented by the people who know them best. Of course, we're very proud to have been able to participate in these projects, but the main thing is to really dig into the engineering, learn about the challenges they face and how they were overcome, and hopefully gain something that's useful to all of us in our profession. So with that, I'm going to, I should first say a little housekeeping. Do feel free to submit your questions through the chat as they come up. And at the end of the presentation, we'll go ahead and read those off. Looking forward to a great presentation. So with that, I'll turn it over to our guest speaker, Eric Pheifer, with Biggs Cardosa. Eric, please take it away.
Great, thanks, Ted, and thank you everybody for joining today. I'm Eric Pheifer with Biggs Cardosa. I'm a principal and vice president there. We are a structural engineering company of about 100 people based in California, headquartered in San Jose, and then we have an office in Washington too. So we do all structural engineering, but our focus is bridges, and one of my focuses has been grade separation projects, and that's what we're here today to talk about. So I'm excited to get into it. Let me share my screen here. All right, is that working, Ted?
Yes.
That's great.
Thanks, Beta. Perfect. So this is the McKinley Street grade separation in Corona, California. I know we've got folks from all over the country here. So Corona, for those of you who are not as familiar with Southern California, is about 40 miles to the east of Los Angeles in Riverside County. There's a lot of freight traffic that goes through here that originates from the ports and goes through the rest of the country. So rail traffic is a real key thing that we typically try to promote rail movement while also improving safety, and that's what this grade separation does. I titled my presentation From Concept to Construction, just because there are some great technical details I want to share with you guys, but it's an unusual bridge type for California, so I wanted to kind of go through the history of the project and some alternatives that were looked at, and then why we ended up with the project we did, which you should be seeing coming on screen right now. It's a steel network tied arch that spans over the railroad and carries McKinley Street up and over the tracks. So I'll go into the history of the project, some alternatives. We'll discuss some technical details related to the arch ribs, the arch rib bracing, some of the bolted connections, and then I'll show you some videos of the bridge being moved into place by self-propelled modular transports. So this is what the project site used to look like. It was an at-grade crossing with BNSF Railway, 2 tracks, and about 100-foot wide right-of-way. And immediately adjacent to that was a flood control channel that had a bridge that carried McKinley Street over. So just to highlight a couple of things, this is McKinley Street. Here's the BNSF railroad tracks. This is the Arlington Channel, and this is Sampson Avenue. So the purpose of this project was, get my pointer off, there you go. So the purpose of this project was to eliminate the at-grade crossing there with the tracks and vehicles and pedestrians to improve safety, improve freight flow, emergency response times, reduce gas emissions, etc. Grade separations are pretty common throughout the states, but I wanted to share a slide that the city had in their June 2017 study session. Basically, at grade crossing, when the gate arms are down, cars are forced to stop and wait for freight trains to pass. Often these freight trains are thousands and thousands of feet long, so the gate can be down for many, many minutes, sometimes 20 or 30 minutes. And so the purpose of a grade separation is to bring the road up or under the railroad, or in some cases the railroad up and over or below, to grade separate vehicular and pedestrian traffic from the railroad traffic. So apart from improving traffic flow, it's really a big safety project. At this particular intersection, there were a number of accidents recorded throughout the years that this grade crossing has been in service, including a number of fatalities. So, really, these projects are great safety improvement projects, and it's really something that I've loved working on. Not only because it improves safety for the area and traffic movements, but it also really helps improve emergency response times when ambulances don't need to wait at the grade crossing or fire trucks, etc. So this site is really, really constrained. In addition to the railroad tracks and the flood control channel and Sampson Avenue here, we also have the SR 91 freeway just to the north. So getting the road up and over and back down before we hit the freeway was a major challenge. There are also a lot of businesses in the vicinity. So, but when we have a project like this, there's a lot of considerations for the bridge structure itself, for utilities, but right of way is also a really key driving factor in grade SEPs. And we want to do whatever we can to help preserve business access and visibility and things of that nature. So that was really paramount as we were looking into this project and developing concepts, is how do we save as much of the adjacent businesses as we can, and make sure that they're compensated fairly, make sure that their access remains after the project's completed. So my contract started in 2018, but before that, the city was looking at a number of different alternatives. One concept was to raise the rail over the road. Now, this would have been an interesting concept in that it wouldn't have touched the roadway at all. It would have kept all the businesses at grade, all the local streets at grade. But the challenge here was the sheer cost of this alternative. In order to get the railroad to be raised and up and over McKinley Street, it would have taken almost 2 miles of embankment retaining walls, track relocations. There was a signal bridge here too, and the railroad just typically is not in favor of raising their tracks. So this was one interesting idea, but unfortunately it never went through. The concept that the city decided to go with was bringing the road over the rail. And you can see here on screen a preliminary concept that just shows a couple things, like a loop road that would connect Sampson and McKinley, a bridge that would take McKinley up and over, some access down into the shopping plazas, and maintenance of Estelle Street here. As we were looking into this, a traditional bridge had a couple challenges, and it kind of led us to think outside the box and look for some potentially different solutions with the bridge and how we'd stage this to limit impacts. And one of the key challenges was maintaining at least one lane of traffic in each direction on McKinley throughout construction. So if we zoom here on the grade crossing, here's a little series of renderings that kind of displays how a typical bridge would be staged. Now we know with a typical bridge, the span length, as the span gets longer, the structure gets deeper. Therefore, it becomes harder and harder to preserve access to the businesses, preserve visibility, and make the connection back down before the SR 91 freeway to the north. So in order to make a traditional bridge work, columns would have needed to land in between the flood control channel and the flood control channel here and the railroad right of way. And BNSF will not permit columns within their right of way, so we were looking at potentially having to relocate the channel. So the way that this would have worked, we would have put traffic one lane in each direction with new crossing warning devices, removed a portion of the structure and started to relocate the channel. That would allow placement of columns where the flood control channel used to be, right outside of BNSF's right of way. That would allow a traditional structure structure depth to be limited and preserve access to the businesses and visibility. But it came with a really serious challenge, which was that there was a partial reduction in the channel capacity. Now, this flood control channel, for those of you who know California, there is a lot of concrete flood control channels throughout the state. And part of the reason is because we just really don't get that much rain in Southern California. And so all the rain, instead of absorbing into the ground, it tends to flood areas. And so we have these flood control channels that carry all the runoff down to the ocean. So a reduction in channel capacity is a challenge, especially when it's undersized. because if this condition were to occur in the wet season, there would be a possibility of pretty significant flooding to the surrounding area. And the challenge with the traditional bridge, right, is that we would have had to do all this work in the dry season. So that's relocate the flood control channel, construct the columns, construct half the new superstructure, get vehicles up on top of the new bridge, and then complete the relocation of the remaining portion of the flood control channel. So without a temporary bridge, without a significant flood control bypass, we saw this as a potentially very challenging alternative, and it caused us to look for other solutions to clear span the railroad, the flood control channel, and Sampson Avenue. That's what led us to a tied arch bridge. So certainly it would help keep the roadway profile down, preserving our ability to maintain access to businesses. We looked into concrete, but ultimately wound up going with steel because of the ability to construct it in a staging area and then move it into place with SPMTs. And initially, the concept was to use a 6-lane bridge with 3 arch ribs. Now, this was very similar to a bridge in the Northeast, I-195 over Providence River. So you can see here it carries 4 lanes of traffic in each direction, or 5 actually, 1, 2, 3, 4, 5. 1, 2, 3, 4. There we go. 4 lanes in each direction. And is a 3-arch rib system. Where the network configuration really comes into play and is a benefit is in reducing the bending moments in the rib and the tie girder, thereby dramatically reducing the steel quantities. This shows a comparison of traditional vertical hangers versus the network configuration, and you'll see here the bending moments for the network configuration are quite a bit smaller. So what that allows us to do is optimize the steel quantities because we're just dealing with axial forces rather than significant bending moments. That's critical in many regions, but it's also extra critical in a state like California where the price of steel is significantly higher. Traditionally, we've done cast-in-place post-tension concrete box girder bridges and precast pre-stressed girders. So steel is pretty uncommon, so we're trying to look for ways to optimize the steel structure, thereby reducing the cost. I wanted to show a couple other samples that kind of guided our concept development here. So this is the Whittier Memorial Bridge in Massachusetts. You'll note it also features some X cross bracing. It was 2 independent separate structures. So we had looked at that, but ultimately decided on a 3-rib structure. The Lake Champlain Bridge on the New York-Vermont border is also a good network arch sample and was a very successful project. And then in California, besides the 6th Street Bridge, which was just completed, the only one that I'm aware of was a Happy Hollow Zoo bridges in San Jose, California. And those were network tied arches, but pedestrian tied arches. So to our knowledge, McKinley is the first vehicular steel network tied arch in California, and was a pretty interesting bridge structure to look at for this project because it solves so many of the engineering challenges. Initially, we were planning on a structure very similar to Whittier or the I-195 bridges in Providence, and those would have featured I sections on their side and X cross bracing. But you'll see later we did some value engineering, dug into the aesthetics a bit more, and came up with a much sleeker structure, in my opinion. We decided that the best way to stage this would be to build it in a staging area and move it into place with self-propelled modular transports, an accelerated bridge construction technique. The self-propelled modular transports have been in use all over the country. They really offer a lot of flexibility in terms of how a bridge can get built in a staging area and moved into place. You'll see here the picture on the left and in the bottom right, those were from the I-195 bridge in Providence that was erected in a staging area and then moved into place on barges and with SPMTs. And then the picture in the top right is the SPMTs from this particular project. So we thought that the ability to build it off-site and move it into place would further help expedite the schedule, reduce traffic impacts, especially to motorists and to rail traffic. So this was kind of the preferred construction staging concept to really help mitigate a lot of impacts and accelerate schedule. The other challenge that we had to solve was how to get this bridge into place and stage construction of the approach embankments so that we could still maintain one lane of traffic in each direction at all times. So the concept here was to build up the west approach. You can see this kind of dirt texture. We would use bent type abutments. So that's a bent sitting directly in front of abutment, a bent or a pier, depending on what part of the country you're in and how you refer to it. But basically the bent takes all the bridge loads, and then there's a small approach slab that spans from the bent over on top of the embankment. So basically the approach slab functions as a mini backspan, a mini bridge. And so by doing that, instead of building a traditional abutment to receive the entire bridge, we could have traffic continue to flow between the columns and underneath the bent cap, and then also come out and utilize the existing grade crossing with the existing crossing warning devices and loop back in. So this method provided us, the method of using bent type abutments as opposed to traditional cantilevered abutments provided us the flexibility to reuse the existing grade crossing, keep traffic one lane in each direction on McKinley without needing to acquire additional right-of-way to build a temporary road or temporary grade crossing. This is what we wound up with going into our 65% design. You'll note that this area on the northeast corner here between the 91 freeway and Sampson is kind of shown in a Tron type pattern. That's because there are a lot of different alternatives that we looked at with respect to that road and how to maintain connectivity between McKinley Street and Sampson Avenue. So I'll go over some of the options we looked at there. But the point is here, we had a concept that we thought would work well given the desire for a 6-lane facility and a loop road with plenty of storage capacity, but ultimately ended up undertaking a significant value engineering effort and continuing to look at the aesthetics of the structure. For the loop road, we had a few different alternatives. I won't cover them in detail in this presentation, but they range from a roundabout that would take traffic around the shopping center to going through the shopping center, a few other different variations, and ultimately these all had significant cost, and there was a desire to continue to look at options. So the city formed an ad hoc committee composed of 2 city council members. They were concerned about the overall price of the project at the 65% level, and were looking for ways to value engineer and see if we could come up with a structure and a geometric configuration that would still serve the project, but would be more in line with the budget that the city had and the funding that they had through a particular Senate bill. So after a couple of meetings and a value engineering session, what was ultimately arrived on was that a 4-lane facility would serve the project well. So instead of a 6-lane facility where we had bikes that were sharing lanes here and pedestrians here, the idea instead was to have a 4-lane facility with dedicated bike lanes and then shift the pedestrians to the outside on cantilevered sidewalk brackets. So the revised rendering of what this looked like is shown here now. So we've got a 4-lane facility, a much tighter loop road. We've maintained the connection still down into the shopping centers and pushed the wall away a bit from the buildings to try to maintain some visibility. So we basically held the west edge from what would have been the 6-lane facility and narrowed it down to a 4-lane facility. This shows the driver's view of our revised configuration here. So with the 4-lane facility, it did give us the opportunity to reduce it from 3 arch ribs to 2 arch ribs. And then there was a real push to kind of improve the aesthetics over what was previously shown. So in lieu of the eye members, the built-up eye sections for the arch ribs, we went with boxes. In lieu of the X bracing, we had some larger jumbo HSS sections for matless tube. And those, I think, really cleaned up the structure and made it look a lot more elegant, along with inclining the arch ribs towards each other. So it became a basket handle network tied arch as opposed to using vertical members. We did go through a few variations too with the public and with city council. So we wound up with this blue that you see on screen here and you'll see in the photos. But we did look at a few different variations like brown and green and white. On the retaining walls, this is tough to see, so just pay close attention to these areas. But we looked at some various patterns to try to match some of the textures that have been used in the surrounding area, and ultimately ended up with what we called the dot pattern, very similar to the SR91 project from a few years ago. So that kind of covers how we got to this configuration, some of the tweaks we made to get the aesthetics looking a little bit better, and some of the variations in the geometrics to really get the project back within the city's budget. Next, I'll go into some of the technical details, which I know I'm sure a lot of you here are structural engineers and will be excited about this. So give me 1 second, and then we'll dive in. Okay, so here's the bridge general plan and elevation. We prepared a pretty exhaustive set of contract documents, including a multi-100-page plan set. But I wanted to just bring up a few of these images to highlight some of the features, some of the technical features of the bridge in more detail. So it's about a 290-foot long network tied arch. The width is about 60 feet, and it clear spans over BNSF, this flood control channel, and Sampson Avenue, with a minimum vertical clearance of 24 feet over the railroad, as required by railroad guidelines. The structure depth is pretty shallow. We spent some time optimizing the floor beam spacing and configuration, and got it down to about 4'6". So that really helped keep the structure depth low, and we really had no flexibility on the vertical clearance over the railroad, but we did have flexibility in the structure depth. So using a bridge type like a tied arch allowed us to really optimize and get the deck shallow so we could keep access to those businesses. It is a basket handle arch, as I mentioned. The arch ribs are box sections. The tie girders are also box sections. Now, one key thing I wanted to highlight here, in a network tied arch project, there's often a discussion about whether the tie girders should be inclined or vertical. In this case, we elected to keep them vertical for ease of fabrication. It does make it a little more complicated at the knuckle section, where the arch rib that's inclined comes in with the vertical member. But we've seen a number of projects where the tie girder is inclined to match the incline of the arch rib, and that works perfectly well too. It just, from our research and discussions, we thought that the vertical tie girder would work pretty well for this project, and I think the fabricator and the contractor did a great job fabricating and erecting the span. Let me erase this here. The other thing I wanted to point out, so we have a number of splices on the arch ribs and in the tie girder. You can see here they're noted as RS2, RS3, et cetera, RS1. So, and then on the tie girder, we separated it into lengths of about 70 feet maximum. So the arch ribs, we were able to get up to about 100 feet, whereas the tie girder, we were much more limited just due to the size of it. We also needed splices pretty close to the knuckle, just because the knuckle has some pretty odd dimensions, and so shipping considerations really come into play when designing the knuckle and looking at where splices should be located such that this can be shipped. The cable hangers are all attached using fin plates. I just highlighted a couple details here, so you can see this is the tie girder section with the fin plates inclined to match the incline of the cable hanger. Just have a few plates here with clevis pins that go through them. These are stay cables that we used. I know there's a bunch of different options when it comes to cable hangers and tensioning. We thought a stay cable system would work pretty well here, and the system that was ultimately selected was the Schwager-Davis system, SDI. The cables all have vandalism protection on them, as well as HDPE sheathing. A lot of protection around these to ensure that they'll stand the test of time and meet all the PTI requirements. We also did a pretty exhaustive analysis as part of our design basis memorandum to make sure that we had looked at various cable failure scenarios. So in one instance, we assumed that maybe a vehicle or something would crash into the into the side of the cables, go through the barrier, which again, these are test level 4 crash tested barriers. So we don't envision that happening. But should that happen, the design criteria was that we would assume failure of 4 cables. So we had to do a lot of additional analyses just to make sure that this structure was safe under extreme event conditions. For the lateral bracing, we used to have the X members. Then, as I mentioned, for aesthetics, for ease of constructability, we ended up switching to these HSS members. I think it made the structure look pretty clean and elegant. Just demanded a lot of rigidity in the HSS members to resist the lateral demands of the structure. Zooming into one of those details there, you'll see here we had the HSS welded to the arch rib and then bolted a few feet off of the arch rib, and you can see an isometric view up here. We use the Atlas tube 22 inch by 22 inch HSX sections. So these are the jumbo product. And these worked really well, but one of the challenges here is that these sections are very difficult to get into and bolt. So we had a lot of blind bolted connections. That's where another Atlas tube product came in and really helped us out here, and that's the Shuriken connections. If you guys have not seen this, I would highly recommend visiting Atlas Tube's website and taking a look. Basically, they solved a lot of the challenges of having bolts that cannot be accessed during field bolting, and in lieu of tack welding nuts, which has some challenges, or gluing nuts, I know there's some other methods. This seemed to work very, very, very well, and it was great working with the Atlas Tube crew on getting this product utilized for this bridge. They can explain a lot better than me, and I'd encourage you to go look at the website, but basically it's this plate that gets tack welded that holds the nut in from the inside so you can bolt from the outside. So that's my very, very basic description of it, and you can see it here used for those HSS 22 by 22 sections. And the arch rib splices here, you can see the shurikens in there. So this product worked very well for HSS sections and for built up sections that still were a bit too small for access. I mentioned that the SPMTs were something we wanted to use. Self-propelled modular transports were something we wanted to use to really expedite construction and limit impacts. So what we had specified in the contract documents was that the bridge should be constructed in a staging area, in the area where the loop road ultimately would go. And then the bridge would move over Sampson Avenue and the flood control channel and the tracks, and then slide into its final position. So we had the staging area, we had a temporary bridge over the Ellington Channel, some track work to protect the tracks during the move, and then once the SPMT lines would get lined up on Sampson Avenue and on the other side of the tracks, it could slide down into its final position. So that happened in August of last year, and it was incredible to see. I'll show you some videos in a moment and just go through the SPMT move and the erection of the bridge. So here's the bridge getting erected in the staging area. You can see here the temporary supports that we needed as part of the SPMT bridge move. The cables are not installed yet, but you can see all the arch ribs are bolted up and in place, all the tie girders, the sidewalk overhang brackets. Once the bridge was fully assembled and ready to go, it was put onto the SPMTs in the staging area and ready for the move. So this was Saturday morning in August. This gives you a close-up of the SPMTs. For those not familiar with them, they are a modular system that comes with a number of wheels. They're remote controlled. The wheels can rotate 360 degrees. Some manufacturers have different specs, but these things are really versatile, really mobile, can support a lot of weight and distribute a lot of weight so that you're not overstressing existing pavement sections or in our case, flood control channel walls. And they're all remote controlled and can allow a very, very heavy structure to be moved from a staging area into its final position. This shows the front edge, the leading edge of the move here. So you can see I'll show a better picture of this in a second, or you'll see it in the video. But in lieu of a full temporary bridge, the contractor elected to use slide tracks. So this actually turned into a combination of a self-propelled modular transport move and slide-in bridge construction. So they moved the bridge from this leading edge of SPMTs, dropped it on the slide tracks, slid it across, picked it back up on the other side of the tracks, and then moved it back into place. So it was a really, really interesting and unique accelerated bridge construction method. This is at night. It was early Sunday morning as the bridge was moving down into its final position. So we're up here on top of the embankment. You can see some of the bent cap here. And here's the bridge on the two lines of SPMTs, and the tracks are right there. So once the bridge got moved over the tracks and started to slide down into place, it went like clockwork from there, and everything got set, and it was a success. So now the fun part. Here's some videos of the move that I wanted to share with you guys, and you can see here that the bridge is in the staging area on the SPMTs, ready to go Saturday morning. So let's play the video. So slide tracks are being installed over the channel and extended out to where they'll be picked up from the SPMTs. The bridge started to move Saturday morning and got right up next to the slide tracks there. Throughout the rest of the morning, they worked on transferring the SPMTs or transferring the bridge from the SPMTs to the slide tracks. You can see it got jacked up a tiny bit there. They're moving the SPMTs out, finishing the slide track work, and getting ready to push this over the channel. So they did the initial push just to make sure everything was working well. During all this, the specs were clear about monitoring for deformation and twists and things of that nature. And the erection engineer had looked at all different steps of the transfer and the bridge move. While we waited for rail traffic to shut down, the bridge inched a little bit closer. Then the absolute work window started. BNSF stopped trains through the area. The bridge continued to slide over the tracks and over the channel and then over the tracks. And then the rest of the about 8-hour work window was spent transferring the bridge back to the SPMTs on the other side. I've got another video for that in a second. And then in a second here, you'll see those wheels rotate 360 degrees and move the bridge down into its final location. The bridge was lowered and set right as the sun was coming up. The work to restore the travel path, Sampson Avenue, all the work done on the railroad was completed, and then the train tracks were reopened. Our public outreach consultant created what they call the hype reel, which I thought was pretty cool. I wanted to share with you guys, and this gives you a few other angles of the move as well. So I'll mute it because it'll be hard to hear the sound, but this shows again that a similar view. Now you can see the full slide tracks there in some of the views. This shows you an overhead of the slide tracks over the channel. This is the other angle that shows the move over the tracks. I'll let it play because it's pretty cool, and interject a little bit less so you guys can enjoy the video. All these are available online if you want to search for McKinley Street grade separation. You'll find the city's website. It has a lot of great project photos and videos. So all in all, a really successful move. Kudos to all involved. The contractor, the bridge move contractor, the erection engineer, everybody involved in making this a successful move. It was a pretty amazing sight to watch, a highlight of my career, definitely a highlight of this project as well. So the next step after the bridge was moved into place was to complete the construction of half of the approach embankments. So you can see here the west side was almost ready to go. They just needed to move the bridge into place on the bent type abutments, then construct the deck and the barriers, and those approach slabs that I mentioned span from the bent type abutment to the approach embankment. And then once that was completed, traffic was shifted up onto the bridge, and the remainder of the embankment is now in process. So I'll show you one one more video here that shows the current status of the project and where we're at as of about a month ago. So you can see here a completed bridge with traffic on it, one lane in each direction. The west approach embankment has been completely done. The bridge is all ready to go. Cables are all tensioned. Everything is functioning well. The east approach embankments are under construction right now. You can see their MSE walls with lightweight cellular concrete backfill. So crews are out there completing that work so that the bridge can open up to the full 4 lanes of traffic in each direction. Or sorry, 4 lanes of traffic, 2 in each direction. We selected MSE because of the speed of construction. We selected lightweight cellular concrete again because of the speed of construction, and so that's all been working well, and the contractor's moving fast to try to get this project 100% completed and open to 2 lanes in each direction. Currently scheduled for late summer, early fall. Work also continues on that loop road, and that should be connected up soon, providing additional access between Sampson Avenue and McKinley Street. So with that, I'd like to say that you'll see why I titled this From Concept to Construction. I wanted to give you an idea of all the thought and alternatives and variations and value engineering and everything that went into this project and led us to arrive at the first vehicular steel network tied arch in California, moved with a combination of SPMTs and with slide and bridge construction. And hopefully soon I'll be able to retitle this presentation From Concept to Completion. But it's been a great project to be a part of. And I appreciate everybody attending today to listen to my presentation, and I would welcome any questions.
Eric, thank you so much. That was fantastic. I'd say, to those attending, if you do have any questions, still plenty of time to get them in the chat. There are a few to start off where we have plenty of time, so figure we can dive in. Maybe first some simple ones. We heard what was the total cost and how many trains per day were there at that location?
Construction costs came in at about $60 million. It was a tough time to go out to bid. We went out to bid in 2021, and that was right when the first round of tariffs hit. And so it was a difficult market to go out to bid in, and our engineers' estimates were not exactly in line. But still, it was the bids came in well enough that the city was able to award the project and continue on with it. In this location, I don't have the exact train numbers off the top of my head, but there's a combination of BNSF railway trains, Metrolink trains, which is the commuter rail here in Southern California, and I think it's somewhere in the range of 50 trains a day, something of that nature.
Okay. One just came in. Who is the GC steel erector fabricator and slide contractor? I assume that means the actual bridge movement.
Make sure I get all these, Ted, because I didn't write that one down. But the contractor is Walsh. The SPMT move contractor was Oxbow. The fabricator was Thompson Metal Fab up in Washington. And then who am I missing?
The erector, but Walsh self-performed the steel erection, correct?
Correct. Yep.
So you got it. 4 out of 4. Let's see. Says what grade of steel tube was used?
You're racking my brain. I got to pull up my plans.
Well, I guess there's kind of 2 questions there. One, which I guess there's the jumbo HSS tubes, the 22 square tubes, which I would assume are A500, but I wouldn't know. But then there's also the built-up boxes.
The built-up boxes were all grade 50 steel. We had looked at weathering steel as a potential long-term maintenance cost saver for the city, but ultimately, because they preferred the blue color over the brown color, we decided to go with just traditional carbon steel and paint it. I know occasionally their weathering steel can be painted as well, but just something, we had enough innovative things happening on this project that we elected not to go that route. And then, let's see here. It's been since 2021 since I looked at all the details. So let me pull up the general notes here and give you an answer on the HSS tubes. You guys can bear with me for 10 more seconds.
Yeah. We in that size, the vast majority of what we produce, the vast majority is A500 grade C.
It is. Yep, it's A500 grade C.
So one question here is coming up, asked about the process of tensioning the cables. What level of force did they have? From which side? Were they retensioned? All that sort of stuff. And I'll add my own addition to this question was if you can talk a little bit about maybe how you went about optimizing the layout of the cables in terms of numbers, angles, that sort of thing.
Absolutely. Let me start with the optimization and go back to the tensioning. Obviously I was the project manager on this. We were the structural engineer of record, but there was obviously an erection engineer involved too. So we went through our optimization, and then the erection engineer did their own optimization as well to arrive at the final stresses. So let's go back to that in a minute, but let me share my screen again and show you guys kind of the cable hanger layout. All right. So with network tied arches, one of the things that we commonly found where there seemed to be a bunch of different options for how you arrange cables. Some bridges keep a constant angle. So if I were to sketch this on screen here, it would look like that, a constant angle. And then wherever it hits the arch rib, that's where it hits and you make the connection. In our case, when we were doing our optimizations, we found that it was best for the cables to come together at a single point. And that simplified a lot of things for us and seemed to result in better force distribution in the arch rib. But there's a million papers, a million different ways to do this. So if you are looking at a network tied arch bridge and looking at cable optimization, just know that there's a million different ways to do this: constant slope, a fanning pattern, things like that nature. In the case of McKinley, we decided that it'd be best for them to originate at the same point on the tie girder and to connect at the same point on the arch rib. With respect to the tie girder, we wanted all the cables to connect in at the floor beams, so that's where you see these are actually the sidewalk overhang brackets, but the floor beams are behind those. And so what that did was all the force transfer, concrete deck to floor beam and then into the cable hangers, rather than having to go intermediately into the tie girder and then go up a cable hanger. So we found that arrangement really helped optimize bending in the tie girder, along with allowing us to keep our deck pretty thin and maintain a pretty low structure depth. So that's some additional notes about how the cable hanger arrangement was selected, and I wanted to make that note that this is not the only way to do that, just because we went back and forth quite a bit on how we wanted to arrange these cables and did a bunch of optimization to try to find the best way to arrange these cables. Now getting back to the actual tensioning of the cables and that question. So we went through, we used CSI Bridge, and then we had actually ended up doing an independent analysis in a program called Sophistique that a number of you may be familiar with, and looked at optimizing the cable hanger tensioning sequence. And we came up with a sequence that we showed on the plans. It consisted of stressing in a particular order. But I will say one interesting thing about these was the stay cables actually had a ton of reserve capacity for this particular structure. We were not tensioning them anywhere close to their limits, and the structure was also relatively flexible too. So we were finding that there were a lot of different ways to tension and get to the desired force. So really, the use of the stay cable system really helped allow us to have some flexibility and some optimization in the cables, and allow our final forces to be achieved, but then the erection engineer to come in, do their analysis, and come up with a cable stressing sequence that worked really well and arrived at the final forces that were consistent with our design as the engineer record.
Awesome. Let's see. Here's a quick one. Bolts and coating used. Assuming A490. I'll let you. I think I might know the answer, but I'll let you take that one.
Let's see. We had I'm looking at the. Yeah, you probably know better than me on that one, Ted. I'm looking at the issued for construction plans here. So I can't remember if we had to revise these mid-construction, but we had A325 for the high strength bolts. Let's see, grade A325 and ASTM F3125.
Yeah. So this is kind of my wheelhouse, so I'll jump in. But basically, there are two sizes and grades of bolts. The ones in the tie girder, and for anywhere where it was kind of traditional bolting, where the crews could access from two sides. Those were 1.25" A325. And the shuriken, all the bolts with the shuriken, so in the arch ribs and in the jumbo HSS, those were 7/8" A490. That was because that was the largest size available at the time. But since then, we've also released 1 inch. So if it were designed today, it would have slightly fewer bolts.
It would have 1 inch. Yep.
Let's see. There are a couple questions just regarding, the funding. Was it federally funded, state combination, that sort of thing?
So it was interesting. At the beginning of the project, the city actually gave back about $400,000 of federal funding that they had. And the reason for that was that the processes that we need to go through for federal funding, as most of you know, are much more complicated and involved than if it's just state and local funding. So the city actually ended up giving back a very small grant in favor of getting $84.45 million allocated through Senate Bill 132. So that funding it funded 5 different projects in Riverside County, but it did have a deadline associated with the funding, and so that's why there was really a push to kind of get rid of the federal funding and make sure we could just use that state and local, expedite the project as much as possible to make sure that funding was not jeopardized. Throughout the course of the project, the city brought in a few more funding sources, but they were all state and local. The project was never federalized.
Just a question here about whether you considered concrete fill for the arch ribs. And if so, what will be, I guess, how things compared there?
We had not considered concrete fill on the arch ribs in detail. I think that potentially could have allowed us to reduce the dimensions a little bit, but we already felt it was a relatively small section. But it's a good suggestion to look at for those of you who are looking at steel network tied arches like this. We did look at foam filling the arch rib because it's not big enough to be inspected to have a person climb in like the tie girders are. We looked at polyurethane foam filling in order to prevent any potential water intrusion and corrosion on the inside. So I think that's something of interest. If you've got a section that's too small, the concrete filling would work well too, and could be a good solution to look at. And then in the tie girder, this leads me to another point about the tie girder. The tie girder is big enough to be inspected, but in order to make it internally redundant, we ended up post-tensioning each of the tie girders with 4 ducts. And so the reason for that would be to eliminate the tension on the tie girder, remove it from being a fracture critical member, although we did have some fracture critical components in the vicinity of the knuckle. But in general, the tie girder is not a fracture critical member because it was post-tension to be internally redundant. I've also seen projects that use bolted connections between the flanges and the webs to create some internal redundancy. And there's a host of papers and different thoughts on how to make the tie girder not fracture critical or less fracture critical in a tight arch.
I'm gonna add one of my own here. Could you talk for maybe a minute about why the arch ribs were inclined? Was it purely aesthetic? Is there some engineering behind that? How it affects structure?
Yeah, the basket handle was something that after we switched from a 6-lane to a 4-lane bridge, and we just had 2 arch ribs, we realized that there was an opportunity to incline the ribs and create a basket handle arch. It looked pretty good aesthetically, but it also reduced the length of the lateral bracing across the top quite a bit. So that allowed us to then look at the larger HSS, the jumbo HSS sections, which looked a lot cleaner, were pretty easy to install and bolt up versus having to have the X bracing that you saw in the previous concepts. So there are a few different reasons. One was aesthetics. The other was lateral stability and the desire to change to a cleaner lateral bracing system.
Had a couple questions or requests to talk a little bit about the connection of the cable to the box girder. I think there were 1 or 2 sections in there. I don't know if you can maybe pull up the image and just show that.
Sure.
Briefly.
I think it was right around here. So this shows a couple little snippets from our plans here. So we're talking about the connection of the cables to the tie girder and the arch rib. So if I zoom in here, you can see the clevis pins installed in the fin plates. There's two plates on either side. They're offset. And the reason is that one of them goes into the page, one of them goes out of the page, right? So with the cables coming together at a single point. So we had to offset them a little bit and allow then the cables to have the damper and the connections between them. So one of the most complicated parts about this is because we elected to keep the tie girder vertical, we now had a situation where the plates needed to be inclined to accommodate the cable coming in at an angle. And then also there was a bit of eccentricity from the center of gravity of the tie girder, but those were easy to handle in our analysis model, and we just accounted for the offset between the working point of the cable hangers coming in and the center of the tie girder. And then at the top, you can see here the fin plates are similar, and they connect in with a clevis pen as well. I wish I had some good photos to share too from construction, but apart from zooming in on one of these, I'm not sure I've got a great close-up photo of this. So let's see. Let's go to the night photo. There we go. There we go. So you can see the fin plates here, painted blue like the arch rib, the clevis pin, and the fork connection. You'll see some slack in the cable hangers too, because these weren't fully tensioned yet. We had to move the bridge into place first with some partial tensioning, then do another round of tensioning of the cables concurrent with the deck and the barrier placement. All the concrete was done after the SPMT move to keep the weight as light as possible for the SPMTs.
Okay, that's actually a great segue, because we just got a question. Was the overall bridge weight a design constraint for the SPMT system, or is it just a matter of adding more tires?
It's usually just a matter of adding tires, adding units. They come in these modular units, so you can just, instead of using 4, you use 6 or 7 or 8 or however many you need to spread the load out. They all interlock and they're all controlled by one big remote control system. So typically, unless the weights are extremely heavy, in my opinion, that doesn't seem to be a controlling factor on whether or not SPMTs could be used. But it does behoove us to keep the weight as low as possible because these are very, very expensive machines to rent. They are not commonly available. They need to fly all over the country. If there's a day or two delay, in our case here, it could have been, hundreds of thousands or millions of dollars. If for some reason the railroad work window was not open that night, that creates a bunch of challenges too. So just due to how expensive these units are to rent and how challenging external schedules can be in a project, it's best to keep the weight as low as possible. So we elected to move everything into place, or specify that everything should be moved into place with everything except for the cast in place concrete work. So that included all, cables already installed, arch ribs, tie girders. stay in place metal forms for the deck already installed, but rebar not placed, concrete not cast, barriers not cast.
Okay, we're running towards the end here. We'll do one or two real quick more, and then I'll give people a little bit of a housekeeping before we end. First of all, real quick, do you know the software that was used for the renderings?
Yep, I actually did those. So I've been a big proponent of visualization here at Biggs Cardosa, and we use 3D Studio Max. So there's a lot of different software that you can use. You'll see Blender. You can do stuff straight out of Revit or programs like that. We've started making some headway into BIM, but at the time this project was done, or the renderings for this project were done in 2018, 2019, it was all just AutoCAD models, either from Civil 3D or 3D solid models from AutoCAD for the bridge, brought into 3ds Max where they were 3D Studio Max where they were textured and lighting was applied, and then into Photoshop to blend the proposed image with the existing image.
And then the last one I'll ask if you could spend maybe just 1 or 2 minutes on. Someone's asking, what are the seismic considerations? I think we talked about the structure a lot in general. To the extent we can separate gravity and seismic, anything special there?
I was hoping to avoid getting into this because this is probably a whole nother presentation, but we're in a pretty seismically active area, about an hour east of Los Angeles. The peak ground acceleration is a little bit over 0.6 G here. So there's a lot of seismic stuff that we have to contend with, and especially for long span structures, it gets pretty complicated. What we ended up doing for this project, and why I say it could be a whole other topic, is we ended up using seismic protection units. So we had preloaded spring dampers and viscous fluid dampers, all to try to alleviate the forces on the substructures in a seismic event, in the maximum credible earthquake. So I know we're running out of time here, and I appreciate all the excellent questions, but let me just zoom into one more photo just to show you what those look like. So here are the preloaded spring dampers here. So those will press up against the back wall with the bridge now installed into place, and then the lateral ones are the viscous fluid dampers. So we had to spend a lot of time on seismic and look at some special products here just to make sure that we could keep the foundation sizes pretty small in such a high seismically active area. There's a whole host of other topics too that could be discussed about what's elastic and what's plastic in the superstructure. And we here in California design for the no collapse state, so we got to make sure some things perform elastically, some things are designed to perform plastically but not collapse.
All right. So with that, just a few housekeeping things that I say. First of all, Eric, thank you so much for your time, for putting this together, and for speaking with us today. It's a really interesting project. So happy we could have you.
Thank you for hosting me, and thank you everybody for joining and for great questions.
Yep. And then a lot of questions about PDHs. So we will be sending a link to those who attended, where you can follow the link and claim your PDH. And then we will also be posting the video of the presentation on YouTube, and we'll have a link there on the website where you can access that. If we did not get to your question, my apologies. I think we got to most of them, but certainly, there's a link on the Atlas Tube website to get in touch with the engineering team. So if you'd like to follow up with one and submit it there, I'm happy to respond if I can, or we can get a response from Eric. With that, I think we'll conclude it here. Thank you again to Eric and for everyone for attending. I do want to also, just let you know on the Atlas News front, we did recently release our Connections Hub, which is a cloud-based free connection calculator software. Definitely something we'd love to have you guys check out. It's on our website, or you can go to connectionshub.atlastube.com to check it out. Certainly hope that it's useful for you, and if you have any feedback, we'd love to hear it. So thank you again to all, and we'll see you at the next one.